I talked about gem zircons, where they come from, what they look like, and how sparkly they are, etc. last time. And I sort of threatened with the fact that zircon also has both commercial and lots of scientific uses. And so that's what I'm going to start talking about this week. And I'm starting with the commercial side. And so if people join a little bit later, it's not going to be the end of the world as far as following along when we get to the science. Anyhow, this micrograph of zircon crystals and granites should look what's the word I'm looking for? This is my head not working these days. Should look familiar because I showed it last time. And this is just sort of a reminder that zircon is formed from crystallization out of magma. And while gem zircon is usually formed in pegmatite pockets, zircon crystallizes primarily as an accessory mineral, little tiny crystals in all igneous rocks, all kinds of igneous rocks, rhyolite, gabbro, granite, you name it. And so the vast majority of zircon crystals that we're looking at are spread throughout the Earth's crust. They're spread everywhere. And because the crystals are extremely durable, they end up in both metamorphic rock and eventually in sedimentary rock, even though they started out in igneous rock. So that's the real thing to remember. Zircon crystals are everywhere. You can't get away from them. All right, so zircon production. And I showed this slide on the left last time, or this picture last time. That's a zircon mine in Australia. And one of the reasons that that zircon mine is economically feasible is that mixed into that sand, which has zircon in it, is also a mineral called ilmenite. And that's the ore of titanium. And it's really the titanium which is the more valuable product. And so the zircon is essentially a side product of titanium mining. In any event, mines like this, and a bunch of them around the world, and you can see, and let me see if I can remember how to get rid of the stuff that's annoying me in the picture. There it goes. You can see from the circle on the right, all of the countries that are listed, and the two biggies are Australia, that has the lion's share, in South Africa that I mentioned last time. And production from all of these countries has pretty much stayed the same, as you can see, for at least the last half of the 20 teens, except for Mozambique. And Mozambique is becoming a bigger and bigger producer. And so we're talking about zirconium concentrate, where zirconium is basically 40%. And so that 1.4 million metric tons is really about 3 million metric tons of sand. That's a lot of sand. All right, so what does industry do with all that sand? And the answer is in this pie chart. And you can see that there are basically 4 major uses. One of them I'm not going to talk about, the chemical industry, because it basically takes that sand and converts it into other stuff. So that zircon is a major source of hafnium, which is used in the nuclear industry. And then zirconium oxide and zircon itself are used in all sorts of places. The ceramics industry uses a little zircon as zircon oxide, converts it, but for the most part, the other 3 industries other than chemical actually use the zircon as zircon and don't mess around with it. The easiest one to understand is the foundry industry. And as the picture shows, the zircon sand is used for sand casting, investment casting, and all sorts of other types of casting. It's basically ground up really fine. It's cleaned up until you end up with nice, round, consistent grains. And if you do that, you can bond the material together with inorganic or organic binders so that it makes a really solid mold. And that mold is thermally stable, even at very high elevated temperatures. It has high thermal conductivity. So when you pour metal into the mold, it cools off relatively quickly compared to making a mold of something else. And the molten metal doesn't wet the zircon. They're incompatible. And the sand is easily recycled, so you can use it over again after the whole process is done. So that's a really easy one to understand, and you can see all of the physical properties of zircon, these little tiny grains that makes it useful for most of the other applications I'm going to show you. The refractory industry uses zircon as well, except as you can see in this picture, the zircon is no longer that dirty brown color. The refractory industry really cleans the zircon up because they want the absolute highest possible melting temperature when they turn that zircon into bricks, which is the primary use in the refractory industry. And so it's used to line the furnaces that are used in glass and metal manufacture, but it's also used in a number of smaller areas like refractory mortar, where you're trying to stick bricks together that are going to experience high temperature, or in grouts, and you'll see why that's important in a bit. And then also in actual manufacturing of parts for all of these other things.
Steve, could you put that on full screen?
Oh, yeah. Did I forget to? I thought I did that. It must have gone. Okay, I'll catch up in a second here. Sorry about that. Somehow it got lost.
It's okay.
All right, so I was here, and now I'm going on to the next one, ceramics. And ceramics actually takes up more than half of the total production volume of zircon sand. And most of that is used in tile production. And those are tiles that are stuck on the outside of a building. And they basically make that outside of the building indestructible as long as you use refractory grout in between the tiles to keep it all together. And so that's why the two industries work in tandem. Now, there are other traditional uses in ceramics for zircon. It's used as the abrasive and cutting tool, so you can cut tiles to size, but it's also used in the production of the glazes that are making that tile white, and in enamels, and then all other kinds of colored pigments as an opacifier to make those pigments opaque. And then it's also used because of its other properties in advanced applications. And a really interesting one is medical implants. Most people think of those as being made out of titanium because titanium, it doesn't interact with the body, but neither does zircon. And so a lot of medical implants are made out of zircon, usually in the form of zircon oxide, which is why there was that little arrow next to the ceramics industry segment. And the same thing is true in advanced technical ceramics. That zircon is turned into oxygen sensor parts and oxide fuel cells, because you can make them like the Fritz, you can make them basically So they've got holes in them, and small molecules will pass through the different parts of a fuel cell. Anyhow, that's enough of the commercial part, and hopefully lots of other people have joined, or at least the people that are going to join have joined, because now I'm going to start talking about the science. And I mentioned when we were talking about how zircon is formed, that it's never pure. It's a high field strength element, and so it gets concentrated in the last of the magma to cool with a lot of other high field strength elements, like hafnium and thorium and uranium, and then the rare earth elements and the pseudo rare earth elements, as well as niobium and tantalum. And zircon always contains traces of all of these elements, usually with the exception of hafnium in the 1 to 1,000 approximately part per million range, where 10,000 parts per million is 1%. And so zircon is useful, not because it's zircon, but because it contains all of these trace elements in it. And we can, because zircon is everywhere, we now have all of these trace elements everywhere that we can use in all sorts of methods to do all sorts of things. And that's what I'm going to talk about. So where are those trace elements? And I've shown the periodic table, but then I've also surrounded that with a blow up of the elements, the trace elements that I'm talking about. And so all of the yellow elements, the three on the vertical part on the left, those are the pseudo rare earth elements. And then the rare earth elements are the yellow ones across the rest of it. The zircon and all of its near neighbors are high field strength elements. And then you've got thorium and uranium as well. And they're pretty much like lanthanum as far as, or like the lanthanide series as far as why they're trace elements. They're high field strength elements. Now, just as an aside, I thought I would show this slide. All of the high field strength elements, including the rare earths and the pseudo rare earths, are really not so rare. This is a graph that shows the elements sort of normalized against silicon. And you can see all of the mafic, the rock forming elements, and the felsic rock forming elements in that green area up at the upper left. And then you've got the really rare elements down here at the bottom, things like palladium and osmium and iridium, and even gold sort of makes it. But then all of the lanthanides and the other trace elements I was talking about are in that middle section. And if you look and see what else is in that middle section, you've got copper and nickel and zinc. And so the rare earth elements are about as rare as those. And so that's one of the reasons that they end up as trace elements, because there's really a lot of them around. All right, so I'm going to talk primarily about an area of science and an area of geology, actually, called geochronology. It's the science of dating materials and geological events. And it plays a central role, as you can see from the little yellow circles, in essentially all of the historical aspects, how and when things happened in both planetary and earth sciences. And there's a wide range of tools and methods that are used in geochronology. And using those tools, you can date materials and processes that are from billions of years old to those that occurred essentially yesterday in geological time. Now, zircon plays an essential role in all of geochronology, and it's so central that it's got its own name, zirconology. And so that's actually a branch of geology that you can study in graduate school and you can get your PhD in it. And basically all it is learning all of the methods that use zircon crystals in rocks for geochronology in various ways. And so this is the real key to zircon's utility. It has growth rings. If you look down at the bottom, basically what you see in the left panel, the big long one, is 3 different kinds of microscopes looking at the same crystals. So you've got a simple optical microscope in the left side, and you have this very fancy scanning electron microscope with cathode luminescence detection on the right. And if you look at a crystal with that kind of a microscope, you see the pretty ring structure on the far right. So basically what happens is zircon crystals grow slowly as the magma in the crust cools. Those crystals can last for hundreds of millions of years, and they can survive many geologic events. And the crystals can get chipped and broken and remelted, but basically the zircon core remains unchanged. And so it preserves the time at which the crystal zircon originally solidified. And then the timing of all of the geologic events that occurred during the rest of the crystal growth of that single crystal are recorded in concentric rings around the crystal core, just like tree rings. And so if we can extract absolute times from that information in the core, we can get information about when the zircon was formed and all of the geological events that occurred during the rest of its crystal growth. So how do we do that? And the answer is we use radiometric geochronology or isotopic. I use isotopic because that's Don's favorite word. I gave this whole series of lectures talking about isotopes and how to use them in meteorites and in all sorts of other ways. And then Don's final question after I was done was, what's an isotope? So I'm going to tell you about what's an isotope in just a minute. I'm going to start there, and it's thanks to Don that I'm doing it. Anyhow, if you have a radioactive parent atom and it's incorporated in the structure of a mineral when it crystallizes, over time it decays into a stable daughter isotope. If you can measure the concentration of the parent and the daughter in that mineral, and you know what's called the half-life of the parent, how long it takes for the parent radioactivity to decrease by a factor of 2. And that's a constant for any parent because it's a nuclear process we're talking about. So the environment of the atom involved, the chemistry of the atom involved, none of that affects that radioactive decay process. And so the important thing is that zircons contain many, many different useful parent-daughter isotopic pairs. And so if you have a crystal and you can blast it and then measure certain atoms that are blasted out of the spots in that crystal, you can get the ages of the zircon at those 2 sites. And for this crystal, you can see that the ages are something on the order of 20 million years apart. That means that that crystal grew from the core, where the central spot is, to that outside diameter over a period of about 20 million years. That's a lot of information if we know where we got the zircon crystal, and that's always the case. We have to relate all of this time information back to the geology where the crystals were formed and found. Anyhow, I'm going to go back to something that most of you have heard about but may not really understand, to explain how all of this radio dating is going to work. And I'm going to use carbon-14 dating, and everybody's heard of carbon-14 dating. It was developed by Willard Libby when he was at the University of Chicago, first as a wild idea that he published actually in 1945. But by 1947, he had done the experiments to show that it was really practical, even though at that time, the instruments really were not up to the task of doing a very good job of radiocarbon dating. And I got to tell a side story as usual, because Willard Libby eventually moved to the UCLA campus, and he actually had laboratories in both earth sciences and the chemistry department. And when I was a brand new grad student, I was sort of getting my bearings, and I was walking around the chemistry building, which was multi-floored and had lots and lots of labs. And I walked by one lab just as there was a huge explosion in the lab. And of course, I had to walk in to see what was going on. And it turns out that it was Willard Libby's laboratory, and two of his graduate students were trying to make their own homemade root beer. And they blew it up at the carbonation step. But I got to know the graduate students because of that incident. And I got to know Willard Libby pretty well over the time period that I was in the UCLA graduate program. And so, as usual, I have a personal connection to all of the science I get interested in over the years. In any event, back to radiocarbon dating. If you look over on the upper left, there are three different atoms of carbon, carbon 12, 13, and 14. They're all carbon because in the nucleus they have 6 protons. But they're 12, 13, and 14 because they have different atomic weights, because they have different numbers of neutrons in the nucleus. And that's what makes them isotopes, the difference in neutron numbers. Now, we know the relative abundances of those 3 carbon isotopes in nature. Most of it's carbon 12, about 1% of it's carbon 13. And in the picture, it says carbon 14 is less than 0.1%. And that's a bit of a misnomer, because if you really know the number, it's about 1 atom in a trillion carbons, as in not a whole hell of a lot of carbon 14. In any event, we do know the relative abundance of the 3 kinds of isotopes. And the important thing is that carbon 14 is radioactive, and it gives off a beta particle and turns into nitrogen 14. And nitrogen 14 is the daughter. Okay, and so how do we do this? If you look over on the right, what you see is that if you start with a certain amount of carbon 14, and obviously that's a ridiculous amount, you'd never find that much carbon 14 anywhere, but it makes the numbers easier. If you wait 1 half-life, that 10 grams of carbon 14 has decayed away, and now you only have 5 grams. And then if you wait another half-life, you go from 5 grams to 2.5, and then another half-life, 1.25, and so forth. And we know the half-life precisely because we can measure that curve very, very precisely. And the half-life is 5,730 years. So what good does all this do us? Well, if we have living things like an animal or a tree, as they're living and growing, they're absorbing carbon. And that carbon contains carbon 14, as well as the other 2 isotopes. But when that tree dies or that animal dies, and say a piece of wood gets buried or a bone gets buried, no more carbon 14 because the bone doesn't keep making more of itself, organic stuff. And so the carbon 14 stops and starts decaying away to nitrogen 14. And so now we're back on this curve. And if we can measure how much carbon 14 we started with, or figure out how much we started with, and then figure out how much carbon 14 there is at the end, like now, we can figure out how long that bone has been buried or how long that piece of wood has been buried. So what we do is we measure the carbon 13 in that material, because that doesn't change, it's not radioactive. And we can calculate the initial amount of carbon 14 that thing had because we know the abundance ratio. And then we measure how much carbon 14 is there now. And we can figure out how many different half-lives have occurred since death. And that gives us, from a simple ratio, the age of what we're looking at. Now, there's many ways to do the actual carbon isotope measurements. As I said a long time ago, we couldn't do it very well. We can do it very well now, but it's really, really hard. I mean, people throw off, oh, let's measure carbon 14 in the TV shows, like you can do it any old day of the week. But it's incredibly difficult because we're talking about starting with trillions of atoms that we want to look for and ending up with even fewer. On top of that, the assumption for living things is that the air has a reservoir of carbon 14 that gets incorporated with the rest of the carbons, because carbon 14 is made through cosmic rays impacting nitrogen 14 in the atmosphere. And so that should be made at a constant rate. And it essentially has been. The problem is we've done stupid things to dilute the carbon 14 by releasing CO2 from fossil fuels. So those fossil fuels have been dead for ages. And all of a sudden, we've diluted the carbon 14 with massive amounts of carbon 12 and 13 that shouldn't be there. And then we've blown up atomic bombs in the atmosphere. And as a side product, they produce carbon 14. And so all of a sudden, we have to make correction factors for all of those things in order to get a really accurate date from carbon 14 dating. But we can check the accuracy of the dates we get from tree ring chronology, which is called dendrochronology, by looking at pieces of wood that are growing nearby and all of that sort of stuff. And then there's another technique that's sort of internal, using thorium-230. And remember, thorium is one of the high field strength elements that ends up in zircon. And so we can use zircon and the thorium in zircon that ends up in coral as part of the chronometer for checking carbon 14. So all of this stuff circles back on itself. And it used to be that carbon 14 was not too bad for about 30,000 years old, and then 50,000, and then 60,000. And now that we've got better instruments, we can actually measure dates that are as old as 70,000 years with pretty good precision. So what's all this got to do with zircon? Well, first I got to show you, when I talked about the fact that these measurements are not easy, these are the kinds of instruments that are used to measure carbon 14 and do carbon 14 dating. And if you look at the red arrow on the left, you can see that these beasts are used not just for carbon 14, but to measure all sorts of pairs of parent-daughter isotopes that are used primarily in cosmology. So in studying the solar system in particular. And the one on the upper right is the kind that you would use for carbon-14. But if you really want to do a good job and push the technology out to that 70,000 years, then you got to use this beast that fills up a whole room. And the beast looks a little different than the one in the upper right, because that big beige cylinder behind the red box really belongs on top of the innards. This is a picture that was taken when this particular instrument was being serviced. And obviously that's a pretty elaborate process and you don't do it too often. And if I remember correctly where I got this picture from, this is an accelerator mass spec from the Argonne labs. Anyhow, back to zircon. In the case of zircon, we use uranium. Remember, uranium there's a lot of uranium in zircon. And so that's a pretty good start as far as the parent is concerned. And we go back to the formation of zircon, because that's key. Zircon incorporates uranium because uranium is a high field strength element, but it rejects lead from its crystal structure because lead is not a high field strength element. And so almost all zircon has lead in it, but that lead is down in the part per trillion level. And we're talking about uranium that's starting out in the part per million level, usually about 1,500 parts per million. So we don't have to worry about lead that is there from other processes. We just have to worry about the lead that gets formed by the radioactive decay of the uranium that the zircon starts with. So the method development began in about 1907, and it's pretty well established these days. And it's used for dates from about 1 million years to about 4.5 billion years. And the abbreviations for million years ago are MA, and you will see 4.5 billion as either BA or GA in most publications. And the precision, even at 1 million or even at 4.5 billion, is still much less than 1%. Most of the time it's in that 0.1% range, which is pretty damn good. And the technology is widely used for dating all kinds of different geological materials and processes. And the kinds of processes I'm talking about can be things like metamorphic changes in rocks or tectonic plate movements. You know, those are pretty slow, but we can still monitor that process using zircon dating. And the reason that we can use uranium to do all of this is because it has a really long half-life, almost 4.5 billion years, and the age of the Earth is only 4.5+ billion years. So pretty much all the uranium U-238 that was made is still around, or at least a lot of it is. It hasn't gone through many of those half-life cycles. The other good news is that even though this is a very complicated decay chain that I'm showing in the little diagram, uranium has the long half-life of the group. So it's controlling as far as starting with uranium-238 and ending with lead-206. All right, so what do? There's a zircon crystal. We take spots across that crystal and we ablate those spots. We vaporize basically what ablation means. We vaporize material. We capture that material and send it through one of those giant mass spec things. But in the case of zircon, we measure 4 isotopes, not 2, because zircon is really kind to us. It has an internal correction system because it has uranium-238, which goes to lead-206 with 1 half-life, and uranium-235, which goes to lead-207 with a different half-life. And so we can use one of those against the other as an internal correction system for the one thing we have to worry about in doing all of this radioactive dating, and that's the loss of lead during geologic events. Lead has the nasty habit of disappearing from a zircon crystal if it's heated more than 900 degrees C. And so just like there had to be a correction for burning fossil fuels, there has to be a correction for lead loss over geologic time. Now, to do all of this correcting, etc., we make what's called a Concordia diagram. And so what you have in this diagram is the theoretical age curve, that really pretty curve that starts at 0 and goes all the way up to the other corner. And then we plot what's called a discordia chord, as in nothing sits exactly on that beautiful theoretical age curve. So what we do is we take samples across from the core out through the rings on that zircon, and we zap each of those spots and we plot the value we get in this funny kind of plot against plot of the 2 different half-life processes. And it turns out that if you do that, what you get is a lower intercept where that chord crosses the theoretical circle, and that's the time of the disturbance. That's when whatever the geological process was heated up the zircon crystal and we lost lead. The other end, that's the crystallization age of the zircon core. And I'm not going to try to go through all of the fancy math to prove all of this to you. That's the part I'm leaving out, and I'm sure you're all overjoyed. But take my word for it. This is the kind of diagram that's routinely used in geology for almost everything. So here is an early modern dating instrument. And of course, we've got more acronyms. We've got SHRIMP. That is the ion microprobe. That is the zapper, if you wish. That's the thing that vaporizes the spot on the crystal. All right. And then we have an ion mass spectrometer, and it's a SIMS, and it's actually got more names: large diameter, double focusing, secondary ion mass spectrometer. And I picked this particular instrument and shown you that particular Concordia diagram using that instrument, because as you'll see in a minute, Australia is really important in the history of zircon dating. And I'll explain why in a minute. But again, what you have on the left are different crystals. You've got groups of 6s and groups of 7s and groups of 8. So all of these zircon crystals come from essentially the same rock. And we can assume, because they're in the same rock, that they were all produced at about the same time. And we take a whole bunch of spots and we make a really good plot. And what we find out is that they all cross the theoretical curve line somewhere around 2.65 approximately. But that's not important for this picture. On top of that, nowadays, we don't have to use that shrimp machine. We use this much more compact instrument. And you can see it's called the laser ablation inductively coupled plasma mass spectrometer, another mouthful. And it talks about the fact that you use a laser, and you can see it over here on the ablation stage, to zap the crystal in the spot we want. And then we feed that as a plasma into a very fancy new kind of mass spectrometer called a quadrupole mass spec. So it's not that double focusing thing that takes up a whole room. It's this little tabletop gizmo. And again, part of my story, I ended up at Los Alamos with a group that was doing a lot of this kind of measurement. And so I got involved with one of the first commercial quadrupole mass specs available to science outside of the manufacturer's laboratories. And I got to play with it when I was at Los Alamos over a good number of years. And one of the first papers I published out of Los Alamos had to do with mass spec and heavy metals. Not uranium, because I still had platinum compounds from my days as a graduate student. And I had been banned from doing further work at UCLA on their double focusing mass spec because I destroyed the probe end of it by coating the probe end of it with platinum in the process of getting a sample into the sample chamber. And they didn't like that, so I was banned from that. But this machine was very amenable to me using my platinum samples. In any event, this makes uranium and lead measurements really easy because it's very useful in particular for heavy atoms. And so this is the workhorse these days. And in fact, you can take that stage where the ablation is done with the laser, and you can actually turn that into one that has a turntable. And so you can line up a whole hell of a lot of samples on a turntable, and then just like high throughput, turn the table, zap, turn the table, zap, and keep sending these things through the mass spec. And you can get a lot of data in a hurry. And so that's exactly what the geologists did. And in particular, the geologists that were interested in a branch of science called petrology. And I apologize, but I'm taking a quick look to see if I still have an audience or whether I put you all to sleep. So I see Don. Is anybody else still with us, Don?
I'm here.
Yeah,
Oh,
there's
we got a whole bunch of people. I'm not
there's
gonna,
11.
so that's a whole bunch for most of my talks. I'm not going to worry. All right, I'll get back to it then. Change my glasses. So petrology is the study of the history of rock formation. And one of the key things you want to know, especially about old volcanoes, for example, that produce granite, is when did those magmas from those internal volcanoes or the surface volcanoes actually happen? And the volcanoes are old and not active anymore. And so all we've got are the zircons in the rocks. And so the petrologists, when this kind of dating became common enough, the petrologists went berserk and they started finding zircons in every rock they could find around the world, and they started dating them all. And so I've just thrown up a number of examples. In the early days, because the techniques weren't very good, they found young rocks. That's the only stuff they could date. And so on the upper left is granite. And we're not talking about the granite, we're talking about the zircons isolated from the granite. But they did that, and they ended up being able to date that zircon, and therefore that granite that came from some kind of magma event at 333 million years old. All right, and then it doesn't have to be granite. They used it on gabbro, and I can't remember where Ackerberg is, but somewhere up in the Scandinavian area, and I can't remember exactly which country. And so they did that one, and lo and behold, the methodology is better. And so now they're going back and they're really pushing it. It's almost 1,700 million years old. 1.7 billion years old is when that particular gabbro was formed. And on top of the internal correction for the two different uranium decay methods, they also were lucky in that that gabbro contained baddeleite. And if you'll remember from my lecture last time, baddeleite is the natural ore of zirconium oxide. And zirconium oxide also has uranium in it. So you can do the same thing with baddeleite. And they did. And they ended up getting an age from the zircon oxide that agreed with the zircon itself. And those two ages agreed. And you can see that they're, like I said, about almost 1.8 billion years. And that's pretty exciting, you know, because people really they knew things were old, but they had no clue exactly how old. And that kind of age, when you think that the age of the Earth is only about 4.5 billion years old, that's really pushing it. And so they kept going. And on the lower left is a sample that they took out of a borehole. They found this gneissic granite in the Ordos Basin. And again, I can't remember exactly where that is, but they drilled down to make sure that they were looking at like the heart of the magma dome after it had solidified. And it was granite. And they did the whole shebang that we've just been talking about. And it turned out to be over 2 billion years old. And then finally, the pièce de résistance. They went to the Huji Pluton, which is a bluff overlooking the Yangtze River. I know exactly where that one is because it's really famous. And they did the same kind of thing as before. And then they did an additional test. They measured the two lead-to-lead ratios as a correction factor. And putting all of that together, they came up with a date that was over 2.5 billion years old. And that becomes important because of suddenly we're looking at a piece of the original continental crust, the original crust of the Earth that was formed in what's called the Archean epoch. And that's pretty exciting because that was the first time anybody knew for sure that's where the rocks, that's when the rocks were coming from. And so back in 1964, when a lot of this work was done, this was the picture of the development of the Earth. These were the epochs. And at the very bottom, you can see the Archean epoch, and it supposedly contains the oldest known rocks and the oldest known fossils. And then below that is the Hadean epoch. And that because it was supposedly the Earth resembling Hades. It had a molten surface and volcanism, and there were asteroid impacts. And it was just this one, I should have put a picture in there, but it's just this one image of the whole Earth as a big boiling ball of melted material. And the Hadean Archean boundary is the time of the Earth's transition from a homogeneous mess, like I was just describing, to a heterogeneous planet with a solid crust. And now we have evidence from that previous slide showing that somewhere in the middle, towards the top, but in the middle of the Archean period, we actually know that there were rocks for sure. And of course, there were a lot of other measurements that allowed us to say the oldest known rocks were really close to that boundary. and that there were fossils from that long ago as well. And then along came the Molybdenum Corporation, and they were doing exploration in a very remote region in the far west of Western Australia. And you can see on the map where I'm talking about, that red arrow points to a place called the Jack Hills. And the picture right in the middle top is actually a satellite view of that particular area in the Jack Hills. And the satellite view is upside down with respect to the direction of the diagram. And on top of that, at the very top of that particular area of Craton, where Craton is a known foundation rock of a continent. So it is the rock that makes up Australia and makes Australia what it is. Just like the Canadian Shield, or what's called the Laurentian Plateau, is that foundation rock of North America. In any event, at the top of the Jack Hills is this little ugly looking outcrop of this sort of slabs. And you can see what the outcrop rock looks like. And then if you take that rock apart and you look at a piece of it, you see that it's a sedimentary conglomerate. So way up on top of this giant granite outcrop from the center of the earth ages ago is this chunk of sedimentary rock. And if you take a zircon, and I've picked a particular one, but if you take a zircon from that Jack Hills conglomerate that I just showed you, and you make a Concardia diagram and you do all of the measurements I was just talking about, this is the picture you get. And so the samples from that one zircon are labeled 1, 2, 3, and then 4, 5, 6. So it's in pieces. And so the outer part of that zircon is only 3.5 billion years old, approximately. But the core is 4.37 billion years old. That's in the Hadean epoch, where it's not supposed to be. That's before there were supposed to be rocks. And there it is. And on top of that, we know that somewhere during the Archean epoch, that zircon underwent another process by which it got heated up and started growing more rings. And it's those outer rings which gave spots 4, 5, and 6, and that's why they have a different age. So we can start correlating what happened to that zircon crystal with all of the geologic events that ended up making the Jack Hills, and suddenly overturning our whole idea of when the crust of the earth was formed, all from looking at that one zircon crystal by uranium lead dating. And this is a compilation of over 250 Jack Hills zircons and the age distribution. And you can see essentially they're all from about 3.8 billion to about 4.4 billion years old. And so this has totally revised the time estimate for when the Earth's crust formed, and our whole picture of how and when the Earth's crust formed. And it gets better. So finally, in 2014, the Molybdenum Corporation had to give up its rights to the Jack Hills, by the way. And now the Jack Hills have become a protected world reserve. Nobody can mess with that part of the world anymore. Preserved for all eternity and the geological sciences. Anyhow, at a Erawandu Hill, just a little bit away from Jack Hill in particular, a zircon crystal. The one on the top left was found. All of these others are from the Jack Hills, and you can see they have dates sort of like old date on the other crystal that I showed you. They're all in about the 4.3 billion year old range. But that crystal has 4.4 plus billion years old, and it is the oldest known material on Earth. And this is an enhanced color picture of that crystal and the spot at which that sample was taken from the core. And so that little bitty crystal fragment of zircon has totally revised the history of the Earth. And it gets better. I was telling Don that I'm going to suddenly show you some pictures of analyses that I talked about in some of my meteorite talks. Oxygen 18 analyses. And this one is pretty straightforward. It's just measuring oxygen 18 in all of these zircon samples. And so this picture is a compilation of dated zircon samples from rocks that cover 96% of the range of the age of the Earth. From essentially now until the oldest of the old Jack Hills. And one of the things you see is that the mantle zircon, the zircon that's made continuously and comes to the surface from the lower mantle of the Earth, pretty much has the same oxygen 18 content across the whole age of the mantle. That hasn't changed. But if you look at the oxygen 18 levels, they're all higher than that, including the ones in Jack Hills. So what does that mean? That means that somehow the Jack Hills zircons, as well as all of these others, got to the surface and were recycled in magma that interacted with a new oxygen 18 source. Remember that melting event that produced the rest of the rings on that zircon crystal I showed you? So in that recycling process, the zircon interacted on the surface, because that's no longer a deep magma process. That happens when surface magma gets hot again and melts zircons that are already on the surface. And what does that mean? That means that those Jack Hill zircons interacted with surface water. So there was an exchange of oxygen in the silicate part of the zircon. And that happened because of the age of the Jack Hill zircons in the Hadean epoch. And that says approximately 200 million years after the planet itself was assembled from all of its constituent pieces, there was liquid water on the surface of the Earth, and maybe even a liquid ocean. And then as a topper, this isn't a 3-isotope oxygen plot where we're looking at oxygen 16, 17, and 18. And we're doing sort of what we did with the uranium lead, except we're doing it with stable isotopes. And I showed this kind of technique a lot when I was in my meteorite talks. And I'm not going to try to explain it all again. But basically, this again shows that the zircons from Jack Hills have the same values as the newer zircons in the Earth's crust as far as oxygen 18 is concerned. And those zircons had to have been on the Earth's surface and interacted with water. So this is just a second kind of proof that that really happened. All right, so let's step away for a second and use uranium dating for a totally different purpose. This is a Concordia diagram for Martian meteorite 7533. You see how all of the stuff I'm interested in comes full circle. That meteorite was discovered in the Sahara Desert in 2011. And so this is a pretty damn new kind of Concordia diagram. And lots of zircons in that sample, and lots of spots from those zircons were measured. And what we get is an intercept at 1.7 billion years ago, and we get an age for the core of the zircon at 4.5 billion years ago, approximately. So what does that mean? Remember how I said that lead loss is caused by something heating a zircon up over 900 degrees? Well, the likelihood, it's not absolutely true, but the likelihood is that's when the impact of something hit Mars' surface and melted a crater and launched the meteorite that's ended up on the Earth into space. And then from that period of time until we found it, a period of 1.7 billion years, that meteorite wandered around in outer space, but eventually came down onto the Earth's surface and we found it. At the other end, what we're looking at is an age of 4.428 million years ago. That's 4.428 billion years ago. That's when the Martian crust formed, because that's what happened. A chunk of something hit the Martian surface and knocked the chunk of the Martian surface out into space. That says the Martian crust formed at about the same time as the crust of the Earth, and also it turns out the moon, because we can do the same thing with moon meteorites, and we have. And so now we have a picture of the whole the history of the whole inner part of the solar system, at least as far as Earth and Mars and the moon are concerned. They were all formed at about the same time in cosmic history, 4.43 billion years ago. And that's pretty amazing. And then not to get sort of overlooked, I threw this slide in. In 2015, and this is for you, Barbara, the Smithsonian team analyzed zircon crystals in the same kind of rocks from Central America and the northwestern part of South America. And by dating both of those rocks, they ended up with a data formation of the zircons in those rocks of 13 to 15 million years ago. And that's basically when the connections between the Atlantic and the Pacific Oceans were severed by the formation of the closing of the Isthmus of Panama. And that significantly changed the previously accepted date, which had held true in 2015. And that date was from fossil records of animals of similar kinds that had gone across the land bridge and when they started doing that. And so not only did it change the date for the formation of the Isthmus of Panama, it changed the rate at which the animal species on the two sides of the Isthmus of Panama actually evolved. And clearly they evolved at least 4 to 5 times as fast as people thought they had, all from dating some little zircon crystals in rocks. Okay, so I've harped on that enough and people must be sick of it. There is more to my talk, and this is the second part that I'm going to talk about today. There's another dating method you can use that uses both uranium and thorium in the zircon crystal. And it's called helium dating, basically. And what you get are helium ages, even though what you're looking at is the production of helium from the decay, the radioactive decay of uranium and thorium. If you look at this scheme, basically when uranium turns to thorium, the first step in its radioactive decay, it produces an alpha particle. And as the decay goes along to produce what we were just looking at, lead-206, in that process, the uranium produces 8 helium atoms. Okay, and so if you can measure the amount of uranium and thorium, and you can measure the amount of helium, what you can do is get a date. Looks pretty straightforward. And a guy named Strutt took a proposal by Rutherford, and he actually figured out how to do that in about 1920 or 25. And so the first ages of zircon crystals were obtained using this system. And Strutt measured ages from a wide range of localities. And he got dates as early as 100,000 years ago for zircons from the side of Mount Vesuvius. And that makes sense because there's lots and lots of volcanic eruptions producing those zircons all the time. And then he got dates as old as about 500 million years for zircons from Ontario, Canada. And that was pretty suspicious because the lead dating method came along, and we knew that that's part of this Laurentian shield I was talking about, a much, much, much older kind of material. So what's going on? And it turns out that the problem is zircon is leaky as far as helium is concerned. And the helium, in the process of sitting there, the helium leaks out of the zircon. And so when we try to measure how much zircon has been produced, we get the wrong answer. And on top of that, uranium-235 decays to lead-207 like we just saw, but in that process, it produces 7 heliums. And then the thorium-232 decays to lead-208, and it produces 6 heliums. And so we've got all of these different parent isotopes producing different amounts of helium at different rates. And that makes life really miserable. And so by the 1950s, we understood pretty well. So this has been going on for 40 years. And in the 1950s, we probably finally got it into our heads that we were never going to use helium ages for geochronometry until we could figure out and correct for the loss of natural helium. So from the 50s into the 80s, people got it into their heads that helium loss was caused by radiation damage to the crystal. So as the crystal got zapped, it produced little passageways and the helium escaped down those passageways. Or the helium was near the surface of the crystal and it escaped from the surface of the crystal. But in 1987, a guy named Zeitler came along and he showed that helium loss was diffusion dependent in apatite. So lots of minerals undergo this same kind of process. They have heavy atoms in them that end up producing helium, and you can use them the same way you can use the uranium-thorium system. In any event, this is called the step heating experiment, and you can see that there are loosely bound heliums and they escape really fast. Those are the orange circles or triangles. And then there's tightly bound helium, and that's the stuff at the bottom. And you can see that as you keep heating it, it doesn't go away. And all of a sudden you get to a certain temperature and bang, the helium starts getting lost. And then it stays at a pretty constant level. And then if you heat it a second time, you'll lose even more of it. And so a guy named Farley in '96, and now we're getting into modern times. Now we're talking less than 25 years ago. Farley developed the experimental basis for using this helium dating method in apatite. And a few years later, a guy named Reiners came along and he figured out how to use the method in zircons. I'm not going to go into all of the correction factors because even I can't follow the math, and I've tried. In any event, people looked at that and said, there's got to be a better way to use this method. And it turns out there is. They use the method in another new branch of science called thermochronometry. And now what we're looking at is not the date at which a mineral crystallizes, but the date at which a mineral cools to the point where helium no longer escapes. That's called the critical temperature. And on the right, you can see the temperature range in this partial retention zone when you're losing a little bit of helium, but most of it is not being lost anymore. And you can see that you can take a whole bunch of different minerals and you get this whole range that you can use for thermochronometry. And zircon is in the mix. And in fact, it's in the mix at a couple of places. But the important thing is that in the case of zircon, there's no helium diffusion loss once you get below a temperature of about 180 degrees. And that loss is minimal until you it gets higher and higher until you get to a temperature of about 240 degrees, and then all the helium just goes away. All right, so basically what we're looking at is the little picture on the left. We measure in the rock the time since the rock cooled below that closure temperature, TC. So what does that tell us? And is it real? So this was Reiner's experiment. He looked at zircons in, I call it tufa, the geologists call it tough, I call it tufa because Los Alamos sat on this huge amount of tufa because there was a caldera from a giant volcano that, God, it started with a P. I can't even think of its name all of a sudden. Pajarito. This giant caldera volcano blew up and just poured ash all over, and magma and ash all over the place. And Los Alamos sat on it, and in particular, the laboratory at Los Alamos I worked at sat on essentially solid tufa. And what is it? It's the ash that's ejected during a volcanic eruption, and then later it gets compacted by some geologic event. But the zircons in the tufa, the tuff, cooled almost instantly. They got blown up into the air. So they went from magma temperatures to atmospheric temperatures before they landed. So almost instantly in geologic time, they were below that critical temperature. And so you would expect to see, just as Reiner's demonstrated, good agreement between, on the left, the uranium lead date for the zircons in that tooth and the helium date in that tooth. And you can see, I can't see unless I change my glasses, but in the case of the helium method, the date is about 28 million years ago. And in the case of the lead method, it's 28.4 versus 28.3. So that whole hypothesis and all of the corrections that Reiner talked about in order to use the technology works, at least in this particular case. So how much tufa is there that you really need to date this way? And the answer is, in certain places, there's a whole hell of a lot. And so another whole new field of geology gets opened up because you can use zircon in this way. and it's called tephrochronology. And basically what you do is you find ash from a big volcanic eruption or a series of eruptions. And that series of eruptions sends down layers of volcanic ash that turn into layers of tuff. And that happens in places like Iceland a lot. But it also happens in our backyard in Mount St. Helens. Mount St. Helens has blown its top and grown and blown its top and grown in many years, over many years. And as it's done that, it's built up layers of volcanic ash. And so why is all of that important? Basically, those layers provide a framework for looking at archaeological finds in that mass of volcanic ash, or even looking at what are called paleo-environmental materials, pollen grains, all sorts of things. And because you can date those individual layers in that ash, you can date the stuff that's in them, that you find in them. And so that becomes a whole new field of science that's being widely used. And it only has started in the last 15 years or so. And it's pretty amazing to think that our poor little zircon crystals are doing all of this. And then I've got one more slide to talk about thermochronometry. And this is another Reiner's example from a 2005 paper. He compiled all of the data of this kind that had been produced for the area called Gold Butte, Nevada. And that's a picture of it on the right, the real thing. And the arrow is the place where all of the zircons and other minerals were found that were used for this compilation. So again, this is an area outside of Las Vegas, and it is a national monument, so it's protected. And it's only the scientists with special permission that get to go in there and grub around for stuff. In any event, the plot on the left has all of the different kinds of data that Reiner's could find. He produced the zircon data, and other people had done the easier stuff. They looked at apatite, they looked at titanate. So other minerals that were found in this, basically, as you can see from the very top of the picture on the left, that whole area is a sandstone. So the zircons in it have been through the ringer. They started out somewhere, probably in whatever made that big cliff in the middle, or at the right, the real high part. And eventually everything got worn down and compressed into sandstone. And then on top of that, what you see is essentially a geological fault where the white arrow is. And so what happened is, sometime in the past, the earth split apart, and the face of that sandstone, to a pretty good depth, got exposed to the air. And so how did Reiner's interpret all of this data? And he said, before about 15 million years ago, all of the zircon was buried. And so no matter what you did, you got essentially the same thermochronological age, right? It was at zero because it still hadn't cooled enough to show that the helium hadn't stopped leaking. And so that didn't help much. But there was a tectonic event that I just talked about, that earthquake that opened the fault. And when that happened, different zircon populations along that face, and you can see the different depths in the different bands on the left, those different zircon populations were exposed to top-down cooling. And so suddenly they did start cooling below the critical temperature. And so suddenly we're getting all of those different ages. And the closer to the surface you found the zircon, the longer ago it cooled. And so for stuff that was still buried, you were still getting essentially the same helium age as before the earthquake. And then afterwards, you started getting all of these different ages at different depths. And then if you look at the far left, you can see apatite. And the apatite helium age never changed, even through the earthquake event. And why is that? Because apatite has a really low critical temperature. And so the temperature of the apatite containing the uranium that we're using for the helium aging, it never cooled to the point that helium stopped escaping. And so in order to interpret this kind of data, you have to interpret geological events associated with where you got the crystals. And so hopefully that's been interesting, and I'm going to stop at that point. And I'm going to stop sharing.
Any questions?
And I'm going to start where I left off this time in part 3 with more techniques, all of which involve using zircon and all of which involve using zircon in this kind of geochronology at various levels and in various ways and for various reasons. And I'm going to show you how some of these technologies actually get started and understood because of meteorites. And so all of that meteorite stuff I talked about that most of you either didn't hear or don't remember is going to come back to haunt you when I talk about part 3.
Thank you, Steve. I'm going to have to go get somebody to go to work, but it's been really cool. Thank you so much.
My pleasure.
Next time.
Take care.
Bye.